The world of quantum mechanics is full of strange and counterintuitive phenomena. It's a realm where particles can be in multiple states at once, where information can be teleported instantly across vast distances, and where the very act of observation can alter the outcome of an experiment. Recently, a team of scientists in China made a groundbreaking discovery that pushes the boundaries of our understanding of the quantum world even further. They've created a Schrödinger cat state, a bizarre quantum phenomenon, and maintained it for a record-breaking 20 minutes. This achievement, a testament to human ingenuity and scientific progress, has sent ripples of excitement throughout the scientific community. It opens up new avenues for exploring the fundamental nature of reality and paves the way for revolutionary technologies that could transform our world. But to truly appreciate the significance of this breakthrough, let's first delve into the strange and fascinating world of quantum mechanics and the famous thought experiment that inspired it all: Schrödinger's cat. This is the story of how scientists in China took a significant step toward turning a thought experiment into reality, and what it means for our future. In 1935, Austrian physicist Erwin Schrödinger devised a thought experiment to illustrate the absurdity of applying quantum mechanics, the theory governing the microscopic world, to everyday objects. This experiment, known as Schrödinger's cat, has since become a cornerstone of popular science, encapsulating the mind-boggling nature of the quantum world. Imagine a cat sealed inside a box. Along with the cat is a device containing a radioactive atom and a vial of poison. If the atom decays, the device releases the poison, killing the cat. However, if the atom doesn't decay, the cat remains alive. According to quantum mechanics, the atom exists in a superposition, a state of being both decayed and undecayed, until we open the box and observe it. This means that the cat, whose fate is entwined with the atom's state, is also in a superposition, both alive and dead, until we observe it. Of course, in our everyday experience, a cat can't be both alive and dead at the same time. Schrödinger used this paradox to highlight the strange and counterintuitive nature of quantum superposition. The recent breakthrough by Chinese scientists brings us one step closer to realizing Schrödinger's paradoxical cat in the lab. At the University of Science and Technology of China, a team led by Professor Zhengtian Liu has achieved a remarkable feat. They've created a Schrödinger cat state, not with a hypothetical cat, but with real physical atoms. Their experiment, which involved trapping and manipulating ytterbium atoms with lasers, is a testament to the incredible precision and control that physicists have achieved in recent years. The team started by cooling a cloud of ytterbium atoms to near absolute zero, the lowest possible temperature where atomic motion practically ceases. They then used a system of lasers to trap these ultra-cold atoms in a specific configuration, creating what's known as an optical lattice. This lattice acts like a microscopic egg carton, with each atom held in place by light. By carefully manipulating the properties of the laser beams, the researchers were able to put the atoms into a superposition of two different energy states, analogous to the cat being both alive and dead in Schrödinger's thought experiment. This superposition, however, is extremely fragile and susceptible to collapsing due to interactions with the environment. The real breakthrough lies in how long the team was able to maintain this fragile quantum state. 20 minutes of superposition, a new record. Maintaining a Schrödinger cat state for an extended period is a significant challenge. Even the slightest interaction with the environment, a stray photon, a vibration, or a change in temperature, can cause the superposition to collapse, destroying the delicate quantum state. Previous attempts to create and sustain these states have been limited to fractions of a second. The Chinese team, however, managed to achieve a remarkable feat. They maintained their atomic Schrödinger cat state for over 20 minutes. This is orders of magnitude longer than any previous attempt, a testament to the team's ingenuity and the sophisticated techniques they developed. To achieve this record-breaking coherence time, the researchers had to meticulously isolate the atoms from any external disturbances. They created an ultra-high vacuum environment within their apparatus, minimizing the chances of stray particles interacting with the trapped atoms. They also carefully shielded the experiment from electromagnetic interference and stabilized the temperature to an astonishing degree. This remarkable achievement opens up exciting possibilities for various fields, including quantum metrology. Quantum metrology measuring with superposition. Quantum metrology is a field that exploits the bizarre properties of quantum mechanics to make ultra-precise measurements. It relies on the principle that quantum systems like atoms or photons can be in a superposition of states, allowing them to sense extremely small changes in their environment. Imagine trying to measure the Earth's magnetic field with a compass. A traditional compass needle aligns itself with the magnetic field lines, giving you a rough estimate of the field's direction and strength. A quantum compass, on the other hand, could utilize atoms in a superposition of states to sense the magnetic field with much higher precision. The long-lived Schrödinger cat state created by the Chinese team could pave the way for next-generation quantum sensors with unprecedented sensitivity. These sensors could be used for a wide range of applications, from detecting minute variations in magnetic fields to measuring gravitational waves with unparalleled accuracy. This breakthrough's impact extends beyond just metrology, hinting at a future brimming with quantum technologies. Implications and applications. A new era of quantum technologies. The creation of a Schrödinger cat state with a 20-minute lifetime is not merely a scientific curiosity, it's a significant step towards unlocking the potential of quantum technologies. This achievement has far-reaching implications for various fields, promising to revolutionize computing, communication, and our understanding of the universe. One of the most promising applications lies in quantum computing. Quantum computers, unlike their classical counterparts, utilize qubits, quantum bits, that can exist in a superposition of states. This property allows them to perform computations exponentially faster than traditional computers for certain tasks, such as drug discovery, materials science, and breaking modern encryption algorithms. The long coherence times achieved by the Chinese team are crucial for building practical and scalable quantum computers. These computers require qubits to remain in their delicate superposition states for extended periods to perform complex calculations. The longer the coherence time, the more complex the computations a quantum computer can handle. The future of quantum technology is bright, and this breakthrough is a significant stride forward. Conclusion: the future is quantum. The recent creation of a long-lived Schrödinger cat state is a testament to the remarkable progress in quantum physics. It's a field that constantly pushes the boundaries of our understanding of the universe, revealing a reality far stranger and more wondrous than we could have ever imagined. This breakthrough opens up new avenues for exploring the fundamental nature of reality, questioning our very understanding of what's possible. It brings us closer to harnessing the bizarre but powerful properties of the quantum world, promising a future where technologies once deemed science fiction become a reality. As we delve deeper into the quantum realm, we're sure to encounter even more strange and counterintuitive phenomena, challenging our preconceived notions about the universe. But one thing is certain: the future of science, and indeed the future of humanity, is inextricably linked to our understanding and mastery of the quantum world. Thank you for joining me on this exploration of the latest quantum breakthrough. For centuries, we have explored the universe using the laws of physics discovered by Isaac Newton and Albert Einstein. These laws have served us well, explaining the motion of planets, stars, and galaxies. Yet, there are realms where these classical laws break down, realms of the very small, governed by the strange and counterintuitive rules of quantum mechanics. Quantum mechanics, the physics of atoms and subatomic particles, reveals a universe vastly different from our everyday experience. Here, particles exist in a haze of probability, capable of being in multiple states at once. This strange world, however, seems incompatible with Einstein's general relativity, which describes gravity as the curvature of space-time, a smooth and continuous fabric. This is where quantum geometry enters the picture. It is a field of theoretical physics that attempts to reconcile these two pillars of modern physics, quantum mechanics and general relativity. Imagine a world where space and time are not smooth and continuous, but are instead composed of tiny discrete chunks, much like the pixels on your computer screen. This is the essence of quantum geometry, a field that seeks to understand the very fabric of reality at its most fundamental level. Unifying quantum mechanics and general relativity is a major challenge in modern physics. These theories are successful but seem incompatible. Quantum mechanics describes the universe as probabilistic and quantized. General relativity describes gravity as a smooth, continuous property of space-time. Quantum geometry proposes space-time is quantized, made of tiny, indivisible units. Like light is both wave and particle, space-time may be granular. Imagine a piece of fabric. From afar it appears smooth and continuous, but as you zoom in, you begin to see the individual threads that make up the fabric. This is analogous to how quantum geometry views space-time. What we perceive as smooth and continuous is actually woven together from tiny, discrete units of space-time. These units, often called Planck units, are incredibly small, on the order of 10 to the power of minus 35 meters, far smaller than anything we can currently observe with even our most powerful microscopes. At these scales, the very nature of space and time becomes fuzzy and uncertain. Space-time itself becomes subject to the same quantum fluctuations that govern the behavior of subatomic particles. One of the key concepts in quantum geometry is the idea of quantum foam. This refers to the turbulent, ever-changing nature of space-time at the Planck scale. Imagine space-time as a bubbling, frothing sea of quantum fluctuations, where virtual particles constantly pop in and out of existence. This dynamic and fluctuating space-time is a far cry from the smooth, static space-time of classical physics. Pioneers of the quantum realm. The quest to understand quantum geometry has attracted some of the brightest minds in physics. One of the pioneers in this field was John Wheeler, who coined the term quantum foam and made significant contributions to our understanding of black holes and quantum gravity. Another leading figure is Roger Penrose, known for his groundbreaking work on the mathematical description of black holes and his contributions to twistor theory, a mathematical framework that could potentially provide a path towards quantum gravity. Abhay Ashtekar, a physicist known for his development of Ashtekar variables, provided a new way to formulate Einstein's theory of general relativity, making it more amenable to quantization. Carlo Rovelli, one of the founders of loop quantum gravity, has made significant contributions to our understanding of quantum spacetime and its implications for the early universe. These are just a few of the many brilliant minds who have dedicated their lives to unraveling the mysteries of quantum geometry. From theory to reality, applications of quantum geometry. Quantum geometry could revolutionize our understanding of the universe and lead to groundbreaking technological advancements. It could impact cosmology, particularly our understanding of the early universe. Quantum geometry could help us understand the Big Bang and the birth of our universe. It could also provide insights into black hole physics and singularities. Quantum geometry could shed light on the information paradox in black holes. It could pave the way for new technologies harnessing quantum gravity. Speculative technologies include warp drives and wormholes, concepts once relegated to science fiction. The future of quantum geometry. Unraveling the universe's secrets. Quantum geometry is a field brimming with potential, holding the key to unlocking some of the universe's deepest secrets. As we delve deeper into the quantum realm, we can expect to uncover even more profound and surprising insights into the nature of reality. The quest to unify quantum mechanics and general relativity is one of the greatest challenges facing modern physics, and quantum geometry offers a promising path towards this unification. By understanding the quantum nature of space-time, we will gain a deeper appreciation for the fundamental laws that govern our universe. We may discover new particles, new forces, and even new dimensions that we never knew existed. The journey into the quantum realm is just beginning, and the discoveries we make along the way have the potential to revolutionize our understanding of the cosmos and our place within it. A universe of possibilities. As we conclude our exploration of quantum geometry, it's important to remember that this is just the beginning of a grand adventure. The universe is full of wonders, and our thirst for knowledge continues to drive us deeper into the unknown. Quantum geometry is a testament to the power of human curiosity, our relentless desire to understand the world around us, from the smallest subatomic particles to the largest cosmic structures. So the next time you look up at the night sky, remember that the universe is not just a vast and empty expanse, but a tapestry woven from the threads of quantum space-time. And within that tapestry lie the secrets to our existence, waiting to be unraveled by the intrepid explorers of the quantum realm. Thank you for joining me on this journey into the fascinating world of quantum geometry. May your curiosity continue to lead you to new and exciting discoveries. Black holes are mysterious objects in space. They are regions where gravity is incredibly strong, so strong that nothing, not even light, can escape their pull. For years, scientists thought black holes were just cosmic vacuum cleaners, swallowing everything in their path. But could they be something more? Could these enigmatic objects actually be sources of immense energy? The answer, surprisingly, might be yes. One way to extract energy from a black hole is through a theoretical process called the Penrose process. Named after the renowned physicist Sir Roger Penrose, this process suggests that we might be able to tap into the immense energy locked within these cosmic behemoths. Imagine for a moment the vast energy potential of such a process. It could revolutionize our understanding of energy generation and potentially power our future explorations of the universe. But let's not get ahead of ourselves. Before we dive into the details of the Penrose process, we need to understand the basic mechanics of a black hole. Join me as we journey into the heart of these cosmic wonders and explore the mind-bending physics that govern them. Black holes form when massive stars collapse at the end of their lives. Imagine the Earth squeezed into a tiny marble. That's the kind of density we're talking about. This extreme density creates an incredibly strong gravitational pull. Anything that gets too close to a black hole is trapped by its gravity. This point of no return is called the event horizon. Once something crosses the event horizon, it can never escape, not even light. But here's the interesting part. Just outside the event horizon lies another boundary called the ergosphere. This region is key to understanding the Penrose process. In the ergosphere, space-time itself is dragged along with the rotation of the black hole. Imagine a spinning ball in a pool of honey. The honey near the ball will spin along with it. Similarly, space-time is twisted and dragged in the ergosphere. This dragging effect is what makes the Penrose process possible. It's within this swirling vortex of space-time that we can potentially extract energy from a black hole. The ergosphere is a bizarre and fascinating place. Here, the very fabric of space-time is distorted by the black hole's immense gravity. Imagine a spinning top, its surface blurring with speed. That's the ergosphere, where space-time itself is whirling around the black hole. Objects within the ergosphere are forced to move, even light itself. They are swept along by the swirling space-time like a leaf caught in a whirlpool. This movement is not due to the black hole's gravitational pull directly, but rather the distortion of space-time itself. Now here's where it gets really interesting, because objects in the ergosphere are moving so fast they have a lot of energy. And because the ergosphere is outside the event horizon, this energy can theoretically be extracted. This is where the genius of Roger Penrose comes in. He devised a thought experiment, a way to tap into this energy through a clever manipulation of physics within the ergosphere. The Penrose process, extracting energy from a black hole. Penrose imagined an object falling into the ergosphere. This object, let's say a rocket, is carefully split in two. One half falls into the black hole, while the other half escapes back out into space. Here's the key. Because of the way space-time is distorted in the ergosphere, the escaping half of the rocket can actually gain energy from the black hole's rotation. It's like stealing a bit of the black hole's rotational energy and using it to propel the rocket outward. This extracted energy comes at a cost, albeit a tiny one. The black hole loses a tiny amount of its rotational energy, slowing down ever so slightly. But for us, the potential energy gain is enormous. While the Penrose process remains theoretical, it opens up fascinating possibilities. It suggests that black holes, far from being just cosmic sinks, could be powerful energy sources. Cosmic energy factories, black holes and quasars. The energy-generating potential of black holes might explain some of the most luminous objects in the universe, quasars. These distant objects shine brighter than entire galaxies, releasing unimaginable amounts of energy. Scientists believe that supermassive black holes, millions or even billions of times the mass of our Sun, power quasars. As matter falls into these black holes, it forms a swirling disk of superheated gas called an accretion disk. Within this disk, friction and magnetic fields generate intense heat and light, releasing vast amounts of energy. This process, combined with the potential energy extraction from the Penrose process, could explain the extraordinary luminosity of quasars. Understanding how black holes power these cosmic beacons could provide valuable insights into galaxy formation and evolution. It also highlights the potential of black holes as energy sources on a scale far beyond our current comprehension. The future of black hole research, unlocking the universe's secrets. The Penrose process, while still theoretical, showcases the incredible possibilities that lie within the realm of black hole physics. As we delve deeper into these enigmatic objects, we are likely to uncover even more astonishing phenomena. Future research, both theoretical and observational, will be crucial to unlocking the full potential of black holes. New telescopes and advanced computer simulations will allow us to study these objects in greater detail, probing the secrets of their energy generation and their role in the universe. The study of black holes is a journey into the most extreme environments in the cosmos. It's a journey that challenges our understanding of physics and pushes the boundaries of human knowledge. And with every new discovery, we gain a deeper appreciation for the awe-inspiring wonders of our universe. A universe of wonder awaits. Thank you and keep exploring. Thank you for joining me on this exploration of the Penrose process and the potential of black holes as energy sources. It's a topic that highlights the boundless possibilities and mysteries that still await us in the vast expanse of space. As we continue to explore the universe and unravel its secrets, one thing remains certain. The cosmos is full of wonder, and our thirst for knowledge will continue to drive us to new frontiers of discovery. Keep looking up, keep asking questions, and never stop exploring the universe around us. For within its depths lie answers to questions we haven't even begun to ask. For decades, science fiction has tantalized us with the concept of teleportation. Instantly transporting ourselves across vast distances, like stepping through a shimmering portal, has captured our imaginations. Remember the Starship Enterprise materializing in a flash of light? Today, we stand on the precipice of a new era, where such fantastical ideas inch closer to reality. Quantum teleportation. The very phrase evokes a sense of wonder, a feeling that we are on the verge of unlocking the universe's deepest secrets. No longer confined to the pages of science fiction novels, quantum teleportation is now a scientific reality, a testament to human ingenuity and our relentless pursuit of knowledge. But before we delve into the intricacies of this groundbreaking achievement, let's take a moment to understand what quantum teleportation is, and, perhaps more importantly, what it is not. Unlike the teleportation portrayed in science fiction, where objects or people are physically dematerialized and reconstructed elsewhere, quantum teleportation operates on a completely different principle. At the heart of quantum teleportation lies a strange and counterintuitive phenomenon known as quantum entanglement. Imagine two particles linked in such a way that they share the same fate, no matter how far apart they may be. This connection, this eerie bond, is what Einstein famously called spooky action at a distance. When these entangled particles are measured, their properties become instantly correlated. If we measure the state of one particle, we instantly know the state of the other, even if they are light years apart. This seemingly impossible connection forms the bedrock of quantum teleportation. Instead of transmitting matter, quantum teleportation focuses on transferring quantum information, the delicate ephemeral states that govern the behavior of particles at the subatomic level. Think of it as transmitting the blueprint, the essence of a particle, rather than the particle itself. For years, scientists have strived to harness the power of entanglement for teleportation, and recently they achieved a remarkable breakthrough. In a feat of scientific ingenuity, researchers successfully teleported quantum information over a significant distance, shattering previous records and ushering in a new era of quantum communication. This groundbreaking experiment involved creating a pair of entangled photons, tiny packets of light, and separating them by a considerable distance. Next, the quantum state of a third photon containing the information to be teleported was carefully measured and intertwined with the state of one of the entangled photons, through a process known as quantum measurement and classical communication. The information encoded in the third photon was instantaneously transferred to its entangled partner, effectively teleporting the quantum state across the intervening space. Unraveling the implications. A world transformed? The implications of this scientific breakthrough are far-reaching, with the potential to revolutionize fields like computing, communication and cryptography. Imagine a world where information could be transmitted instantaneously, regardless of distance. Quantum computers, exponentially faster than their classical counterparts, could be connected across vast distances, forming a global network capable of solving some of humanity's most daunting challenges. Drug discovery, material science, and artificial intelligence could all be accelerated by orders of magnitude. Moreover, the secure transmission of information using quantum cryptography could render traditional encryption methods obsolete, safeguarding sensitive data from prying eyes. Beyond the horizon, quantum teleportation in the future. While still in its infancy, quantum teleportation holds immense promise for the future. As our understanding of this complex phenomenon deepens, we can envision a world where teleportation becomes an indispensable tool in various fields. In medicine, quantum teleportation could enable the development of ultra-precise imaging techniques, allowing doctors to diagnose and treat diseases with unprecedented accuracy. Imagine a future where targeted drug delivery systems, guided by quantum principles, deliver medication directly to diseased cells, minimizing side effects and maximizing therapeutic efficacy. The realm of space exploration could also be revolutionized by quantum teleportation. By transmitting information instantaneously across vast cosmic distances, we could communicate with probes and astronauts in real time, eliminating the communication delays that currently plague deep space missions. A new era of possibilities. The promise of quantum technology. The successful teleportation of quantum information marks a pivotal moment in human history, heralding a new era of technological advancement driven by the enigmatic world of quantum mechanics. As we delve deeper into the quantum realm, we unlock a treasure trove of possibilities, each more awe-inspiring than the last. Imagine a world where quantum computers powered by entanglement unravel the mysteries of protein folding, leading to breakthroughs in disease prevention and treatment. Envision a future where quantum communication networks span the globe, enabling secure and instantaneous communication, fostering global collaboration, and bringing humanity closer together. The possibilities are as boundless as the universe itself. Keep exploring, the wonders of science unfold. The journey into the quantum realm has just begun, and the wonders we uncover along the way promise to reshape our understanding of the universe and our place within it. As we continue to explore the frontiers of science, we must approach these groundbreaking discoveries with a sense of wonder, responsibility, and a commitment to harnessing their potential for the betterment of humanity. The future is brimming with possibilities, and it is up to us to shape it wisely, guided by the principles of scientific inquiry, ethical considerations, and a shared vision for a brighter tomorrow. Let us embrace the unknown with open arms and continue to explore, discover, and innovate, for it is in the pursuit of knowledge that we truly unlock our potential.